Hello guys, welcome to MJ School of Mining and Geology. In today's session, we are dealing with twin planes, types, and their mechanism. Please don't forget to like, share, subscribe, and hit the notification button below so that you keep notified once we upload new content. So what exactly is twinning? So twinning, it's exactly what is happening in human beings, where you now have two or more crystals that are growing together in a symmetrical manner. All right. So this twinning, it's very important to both mineralogists and geologists, of course, because by understanding how the minerals are twinned, okay, they're gonna tell or they're going to have much information about, or they can understand more about the formation properties and the behavior of minerals. Okay, so this is what you call the twinning. So as you can see over here, you see two crystals that are growing together. Even here, the two crystals that are growing together. So this is example of what you call the pyrite, but we're going to discuss these types of twinning in no time. So we've got the symmetry operations that define twinning. We've got the obvious one wherein the crystals are sharing what we call the mirror plane or the twin plane. All right. So or you can have what you call the rotation about an axis. Okay. Or you can have the center of symmetry. Remember, with the center of symmetry, if you put the dot at the center, the distance to each side will be equal. So this is what you call the center of symmetry. And by so adding the center of symmetry, you're going to produce what you call the twin center. So you need to understand these operations because they're going to help you understand what exactly is happening in twinning. All right. So we've got two types of twinning. We've got the contact twinning and the penetration twinning. But now the contact twinning can also be divided into what you call the polysynthetic twinning and what you call the cyclinal twinning. In polysynthetic twinning, it means the composition are parallel to one another, but the opposite is true for what you call the cyclical twinning. So contact twinning, you can tell it means two crystals are in contact with one another and they share something. Okay, so in contact twinning, the twin components share a common surface or a plane, exactly how you've seen what you call the mirror plane. Remember, so I said you should understand those operations because they're going to help you understand the different types of twinning. So when minerals do not penetrate each other, but they share the surface or the plane, and then we call that contact twinning. So this contact twinning, it can either be a polysynthetic twinning. With a polysynthetic twinning, we know this is a diagnostic feature of the plagioclases, and you see the composition that are parallel to one another. The composition are parallel to one another, and when you're rotating the stage, when one phase get extinct, the other one is not extinct, and the opposite will be true. All right. This is what you call the polysynthetic twinning, or what you call the albite twinning, okay, with what you call the 0-1-0 plane. Okay, so the 0-1-0 is their twin plane. Okay, so but now, on the other hand, if the composition is no longer parallel, but still they're in contact, look at this crystal, this crystal and that crystal, they're in contact with one another. They're not penetrating. And of course, now the composition are no longer parallel. Okay, they're no longer parallel. Then we say that is what you call the cyclical twinning. Okay, we call that the cyclical twinning, and it's the best twinning that is seen in what you call the chrysoberyl. Okay, it's found in the chrysoberyl and many other minerals that I'm about to discuss. So this is what you call the cyclical twinning. Now, penetration twinning, on the other hand, it means two or more minerals, they must penetrate Okay, they must penetrate. For example, the storolite. The storolite it's showing this cross twinning. Okay, like this one. Okay, it's a cross. That is a typical example of twinning shown in what you call the storolite. So in penetration, twinning involves twin components that interpenetrate each other's crystal lattice along a specific axis or a plane. This type of twinning is more complex than contact twinning and can result in intricate intergrowth within the crystal structure. Okay, so but now as we discussed about the operation, then these are defined by a twin center or a twin axis. So the penetration, when we differentiate them from the contact, remember from the contact they share the mirror plane, but now these ones they are defined by the either axis, twin axis, or the twin center. For example, this one is what you call the twin axis. This is what you call the Carlsbad twinning with 001 as the twin axis, and it's best seen in what you call the mineral called the orthoclase. Okay, and then we call this a Carlsbad law. Now we have to talk about the interesting feature, that is to say, for you to understand the twinning, okay, you need to understand the laws. Okay, so because even the country it's governed by laws. Okay, so even the twins or the twinning in crystals, they're governed by these laws. So twin laws in mineralogy refer to the specific rules or principles that govern the formation, okay, that govern the formation of twinning crystals. Now, twinning is a common phenomenon in minerals. We know that, and we've already talked much about that. And then twin laws describe the geometric relationship between the twin components and help mineralogists identify and classify twinned crystals. And then these, they can be expressed in the form of HKL, or exactly how you can express them, how you express what you call the Miller index. Okay, so the surface along which the lattice points are shared in twin crystal is called a composition surface. So if you are sharing a plane or the surface, we're gonna call that a composition surface. It means on that plane you are dividing two or more composition, or basically two compositions. Okay, so understanding twin laws is essential, is very important for identifying and classifying twin crystals, interpreting their formation mechanism, and telling us much about the geological process, or deriving, okay, their geological process, okay, or telling us what happened back in the past to these minerals. Okay, so which is why as a mineralogist, or not only that, these twin laws, they are also used by people in material sciences. Okay, even also the deformation defects of these crystals, they're used not only by mineralogists. Okay, so by studying the geometric relationship between twin components and applying twin laws, mineralogists can gain a better understanding about the crystallography and the formation history and the properties of these twin minerals. So of course, I hope up to so far you understand how important are these twin laws. It means they are worth understanding. All right, nonetheless, we start with the twin laws, which are found in what we call the tectonic system, and then these are the very or are the most important twin laws. We talk about Albert law. If you don't want to say Albert law, you can say polysynthetic. Yes, you've guessed it right. And then if you don't want to say a pericline, you can say a tartan twinning. Okay, it's the type of twinning resembling a plate of a Scottish kilt. All right. Yes, so yes. So now with the Albert, we've already talked about it. It's showing the zebra stripes. So when you identify minerals, these are very important for identifying or differentiating plagioclases. If you want to differentiate K feldspars from plagioclase, you need to see these polysynthetic twinning is a diagnostic feature of the plagioclase. So by observing this feature under the microscope or under a petrographic microscope, you definitely know that, oh, this is, I'm talking about the plagioclase. Okay, so you need to understand this. But if you were talking about the minerals such as boma orthoclase or boma sanidine, okay, you need to use what you call the Tartan twinning or the pericline law. Okay, so this pericline law, as pericline twinning occurs as the result of monoclinic orthoclase or sanidine transforming to microcline. So during transformation from orthoclase to or sanidine to microcline, okay, now what's happening now, you're gonna be forming this pericline twinning. Okay, pericline twinning usually occurs in combination with albite twinning. Okay, so it means when you are combining this albite twinning, okay, with albite twinning in microcline, but is now observable with the polarizing microscope. Okay, so it means this type of a twinning, it occurs in simple way when you are combining a pericline and albite. When you're combining these minerals, then you're gonna form what you call when you combine pericline and albite twinning, you're gonna produce what you call the Tartan twinning or the pericline law, or what you call the cross-hatched pattern. So this pattern, it's when it's showing the crosses, we call it a cross-hatched pattern. Okay, or if you don't want to say cross-hatched pattern, you can say Tartan twinning. Okay, so now this Tartan twinning, it will easily help you to know that we are talking about a microcline. Okay, from other feldspar such as orthoclase. Orthoclase, you're gonna use what you call the Carlsbad twinning. So you need to understand this twinning for you to be able to identify the minerals under the microscope. Okay, so microcline, you will see this Tartan twinning or the cross-hatched pattern. Okay, and this twinning, it was, or this pericline law, this pericline law, it was formed when you're combining a pericline and what you call the albite twinning. Now, the other ones in the monoclinic, we have got Manebach law and Carlsbad law. Like I've already indicated that if you want to identify the orthoclases, you just need what you call the Carlsbad twinning. In the Carlsbad twinning, you want to see two different compositions. If you can check here, you've got this one and you've got that one, and now you've got this plane which you call the Carlsbad twin plane. And then even here you can see two different composition. Okay, so if you are now rotating this crystal around its axis, and then you got its axis, you're gonna form along what you call the plane 001, then you're gonna form what you call the Tartan, not Tartan, sorry, but Carlsbad twinning. So forms a penetration twin in the mineral of a clays. Crystal twin under the Carlsbad twinning show two intergrown crystals, okay, one rotated 180 degrees from the other about 001 plane, okay, or 001 axis. Carlsbad twinning is the most common type of twinning in orthoclase, and thus very diagnostic of orthoclase when it occurs. So by seeing this, you know, if you see cross-hatched pattern, you know we're talking microcline. If you see this Carlsbad twinning, you know we're talking orthoclase. But if you see polysynthetic twinning, you know we're talking the plagioclase. Nonetheless, Manebach law forms a contact twin commonly observed in the mineral orthoclase. So orthoclase, you can see it has got different laws that they that can help you identify them. So you can either identify that through the cross-hatched, or you can use what you call the Manebach, which forms a contact twin commonly observed in that. In that. So this twinning is very diagnostic of orthoclase as well when it occurs, as you can see over here. Okay. Now, the monoclinic system, we've got what you call Braveno law and what you call the swallowtail twinnings or twins. If you you like sport, you know the Swallows team. Okay, so the Swallows team, you can tell when they win, you will see there will be dancing like birds, because swallows, it's a bird, né? So it has got the mouth, the mouth, the mouth of that mouth of that bird. It's like this. Okay, it's like that. That is what you call the swallowtail twins. So it shows the mouth of that bird, and you can see like that. Okay, so this is commonly, this is what you call the gypsum, the gypsum. So it shows this swallowtail. Okay, and then the bravano, you find it in what you call the orthoclase. Now can you now see that you need to understand these twin laws for you to be able to identify the minerals. Remember, it's about mineral identification. You can either identify minerals physically and or using what you call the microscope. So now we are dealing with identifying minerals, or the tools we can use to identify the minerals under the microscope. But under the orthorhombic system, we've got the twin laws, we've got the cyclical twins, and we already talked about this type of contact twin. Remember, you know that they are not touching each other. Even beriso, beryl, it's also showing that. All right, so you have seen, and then also what you call the sericide. The sericide is also showing this cyclical twinning. And then last but not least, we've got the Storlight law. You see the Storlight, sorry about that, the Storlight law. The Storlight, you can see that using what you call, it has what you call the cross. Okay, so the mineral Storlight is really monoclinic, but it has a B angle very close to 90, so it has the appearance of an orthorhombic minerals. Okay, so two types of interpenetration twin occur in Storlight: the 031 twins from a right angle cross, and the 231. Okay, 231 and 031. Okay, so I hope it makes sense. Isometric twinning. Okay, we've got the spinel. That is the type of twinning observed in spinel. Okay, that is the type of twinning observed in the spinel. So is a twin plane parallel to an octahedron. It occurs commonly in the mineral spinel. I mean, spinel law in the mineral spinel. Okay, it occurs in the mineral spinel. So you have got this octahedron. Octahedron, it means remember, octa it's 8, hedron it's faces. Okay, so it means this type of a twin plane is parallel to an octahedron. So somewhere here where the two compositions are being separated. Now, and then we can also have what you call the ion cross. Like I said already, what you call the pyrite. So you will see different pyrite or pyrite crystal, or what you call the pyro or pyritohedrons or pyritohedrons. So these are these blocks of pyrite. So these blocks of pyrite, when they are penetrating, they're gonna form what you call the ion cross with the axis 001. Okay, so you need to understand these types of twinning. Now, mechanism of twinning, that is to say, the processes or the manner in which twinning can happen. It can either be a deformation, or what you call transformation, or growth twins. Okay, deformation, I mean, to deform, you are changing the shape of that. Okay, so this type of deformation now can now see we've got these points or these ions or these atoms. Then what you are doing, you are deforming them by applying the pressure. Okay, so and then by so doing, you're gonna shift. Okay, you're gonna shift the arrangement of these atoms. Okay, so can you now see that deformation twinning occurs when mechanical stress or pressure causes parts of the crystal lattice to shift or rotate, leading to the formation of twin boundaries. So when you are applying this pressure, you are creating what you call the compositional plane or the mirror plane. Okay, now the twinning occurs, because remember, by definition, the the twinning can be described using what you call their operations. So when you're applying that pressure, you're going to form this twin plane. Okay, so this type of twinning is common in mineral subjected to tectonic forces or high pressure conditions. All right, high pressure conditions. So for example, you have what you call the spindle in the plagioclase. It's a typical example of the minerals which experience high deformation. I've witnessed this mineral. And my research in the Bushveld complex. Yeah, so I've which is why I'm confident enough that these minerals they are associated with deformation. But this deformation twinning is best seen in the mineral calcite, all right, with parallel lamellars like this one. So calcite, it shows this twinning. It's also called a polysynthetic twinning, but not as the same as that of the plagioclase. So you can now see it's the diagnostic feature of the calcite. So if you want to identify the calcite under the microscope, you have to see this twinning called polysynthetic twinning. Okay, so during deformation, atoms can be pushed out of place, and then if this happen to produce a symmetrical arrangement, okay, so the mineral calcite can be twinned in this way, producing that. Okay, so this twinning is characterized by mainly thin twin lamellars. Can now see they are thin twin lamellars. These are very thin twin lamellars. Okay, so this twinning in calcite is very crucial in intracrystalline deformation mechanism with low critical resolved shear stress and virtually no temperature dependence. So these are very important for you to understand the calcite. Okay, now the growth twins are the simplest ones. These are the type of twinning wherein as the crystal is, remember, we've already mentioned that the twinning happens as the crystal is growing. So as the crystal is growing, a new crystal it's added to the face. Okay, so it's added to the face of an already existing crystal. Okay, now the growth twinning can happen. So it happens as the crystal is growing, and then you are adding new crystal. Okay, you are adding new crystal to the an already existing a crystal. So twinning can occur if the new crystal shares lattice points on the surface of the existing crystal, but it has an orientation different from the original crystal. So they share some they share the lattice points, like how you've seen them, the contact, okay, sharing the mirror plane, okay, or compositional plane. But now when they're sharing like that, it might happen that the orientation might be different. So such growth can be contact twins or can be penetration twins. Okay, so it can either be the two. Okay. Yeah, so the transformational twinning, this is a type of twinning that occurs during the phase transformation. Okay, it happens during the phase transformation, and then in the crystal structure. So as now the crystal is undergoing what you call the transformation, such as the change in the temperature of the pressure, the new crystallographic orientation may form, resulting in twinned crystals. Okay, so that's exactly, for example, the Brazil twin. Okay, the Brazil twin in quartz, and also the Dolphin twin in quartz, and then also the Japanese twin is the typical example of the transformational twinning. So that happens when you are changing the temperatures and pressures, then you are allowing the new crystallographic orientations to form. Okay, so this occurs in the minerals that have very that have different crystal structures and different symmetry at different temperatures or the pressure. So when you are changing the temperature, you are allowing them to form new crystallographic orientations. Okay, so ladies and gentlemen, we are thankful for joining us in today's adventure. It really means a whole lot to us. Keep liking and subscribing to our channel. We're really thankful to your support. Don't forget to like, share, comment, and subscribe so that we keep producing this kind of a content. And for more information, if you don't understand something at all times, you might send me an email on malabatimoraka@gmail.com, or you can comment below, and then we will be happy to assist the way we can. Until next time, cheers.